All right, guys. After 10 hours of didactics, nothing wakes you up more than study design and biostatistics. Woo! So, we're going to go through a brief primer on these two topics, and understand, though, that the American Academy of Pediatrics is not asking you to design a phase 4 clinical trial, nor put together a non-inferiority study. All they really want you to do is understand the basics of some of the clinical studies that we use in a lot of our research, as well as some of the statistics associated with them. It's only 2%, all right? It's only 2%, but you know it's going to be question number 1 on your exam. The talk is divided into two. One, we're going to talk about clinical studies. We'll go over a little bit of the basic terminology, then go into some of the descriptive types of studies like the case series, and then go into the analytics like the case control, cohorts, and trials, and then go over some of the basic statistics that you're going to be asked to do from an American Academy Pediatric exam content. So sensitivity, specificity, predictive values, odds ratios, etc. Now, here's the family tree of epidemiologic studies. Okay, Grandpa over there had 2 kids, one descriptive and one analytic. The descriptive is basically your case series, your case reports, and for the most part, your cross-sectional studies. This is what you do at the beginning when you're talking about something. This is where you actually generate hypotheses. This is when you see something unusual or something new. It starts off with a case report, followed by a case series, and then maybe even a cross-sectional study. It doesn't tell you much except for the what, the where, and what's, and how it, or when it's happening. So they're really useful for rare problems or newly emerging problems. Whereas you go to the analytics side, that's when you're trying to figure out whether or not there is causality. That's when you're trying to figure out whether or not, or why things are happening and how things are happening. Now this, I think we've all seen a graph like this, which basically just tells you the strength of evidence based on your types of studies. With the case reports and case opinions are on the weakest end, but they're also the most prevalent. Whereas you go up, you'll see cross-sectional studies midway through. When you get to the analytics at the top of the pyramid, case control studies are the weakest of all analytic studies because it has the most bias. Followed by that is your cohort, and then eventually your randomized clinical trials. Now the first thing we need to go over is a few definitions. So when you guys are taking your exam, the exam people already know that you're stressed, you're tired, and you're jacked up on coffee. All right, and the first thing we're going to try to do is try to mix you up between prevalence and incidence. Okay, prevalence is the total number in a population at one time, a snapshot. Whereas incidence is the number of individuals who develop a disorder or develop a disease over a period of time. So if I did a study saying how many people in this room have a $5 bill, that's a prevalence. If I then say at the end of my talk, how many people give me $5, that's an incidence of 0. Case fatality is pretty self-explanatory. The number of deaths divided by the number of cases. Now, validity is important, though. You have to understand that that is the likelihood that a cause has a specific and a real effect, and that the internal validity is only really relevant for the analytic studies. So when you're talking about cohorts, when you're talking about randomized clinical trials, that's when validity is important. For the most part, case series and case reports, no one really thinks that they're valid, and they're not trying to describe their validity. But validity is important because that's where you see the bias. And so bias is what affects your validity. There are 3 flavors of bias. Selection bias, where you're not selecting the right subjects, or are the subjects that you're selecting are actually representative of the target population. Measurement bias, which is not just necessarily the test you're using, but also observational bias by the investigators themselves. And then confounding. And confounding bias is intrinsic factors that are associated both with the exposure as well as with the cause. One great confounding is always age. All right, age increases, and that's always can be a confounder, whether or not whether that's associated with the exposure or not. So that can alter the association. All 3 of them can alter the association, leading to both under and overestimation of the real effect. So let's just go through some of these studies themselves. Case reports, most common. Basically, you're describing a rare event. And the study design that you want when you have a rare event or a newly emerging disease, case report is usually, or a case series is usually the first thing that you do. But you have to understand that there's never a control group and you cannot make any causal inferences. So a case report describes a single or a series of instances. The findings are not generalizable and there are no control groups. Cross-sectional studies, though, are a little bit more broad. So they will try to learn a characteristic of a population in a snapshot in time. And it is in the cross-sectional study that we find the best way to determine prevalence. So when you see on your exam, they're asking about prevalence, you're going to be saying, where's the cross-sectional study? The problem is that there's, again, no comparison group. It's just a snapshot in time. And what you will find, you're unable to make causal or temporal inferences, and you cannot measure the incidence. But what you do get is a lot of correlation, despite the fact that you can't make any inferences. A lot of people do. And they say, hey, here's a correlation. But understand that correlations do not imply causation. But a lot of those cross-sectional studies have led to things like the correlation between the people who drowned and the marriage rate in Kentucky. Or the number of people who drowned is associated with the number of Nicolas Cage films. So these are obviously incorrect, but you can see a correlation with them. This one is true, by the way. All right, if you want to imply causation, you need an analytic study. You're going to need to look at observational analytics, like a case control or a cohort study, or you need to go even further and do an experimental design, where you actually say randomized controlled trial. These will actually provide things like incidence. They will provide the cause, the risk factors, and the outcomes. First one we're going to talk about, though, is case control. Case controls are retrospective in nature. That's one reason why, again, when you remember that pyramid, it's the lowest of all the analytic studies. It's retrospective, but it is best used to study rare diseases. So when you have some rare nasopharyngeal carcinoma that only happens 1 out of 1 million, this is best to use to be studied with a case control. You find the cases and then you match them to controls that allow you then to look back in time to see whether or not the exposure of the cases are different than the exposures to the controls. So when you have a rare disease or a rare outcome, that's a case control study. The problem is that with case control studies, it's all about the control group. And that finding and matching the right controls is where, or when you do it wrong, is where it leads to a lot of bias. And so this type of study has a lot more bias than cohorts or clinical trials. You also cannot calculate incidence or relative risk. What you can calculate is the odds. So here's the way that the study design. You start on the right side, or I'm sorry, on your right, with the source population, and you go back in time. Then you define the cases, you define their controls, and then you go back all the way to the left side, and you find out who's exposed between the cases and between the controls. Retrospective, going backwards. Cohorts, though, are longitudinal, and for the most part, they are all prospective. Even the retrospective cohort study basically starts backwards in a distant part of time and then moves forward. So all of these cohorts are prospective in their nature. They can study numerous outcomes. That makes them a little bit better, and they are best for rare exposures. So what you want to do is to say, well, listen, if people who live around a nuclear power plant, do they go on to develop nasopharyngeal carcinomas or something like that? A cohort would be best to go ahead and look at a very specific population and follow them through time to see then if they develop the disease. The problem is that it's extremely expensive and very time consuming. They require a lot of subjects, thus the expense, and a lot of subjects get lost to follow-up, and that's where they are very much limited to. So here's the cohort study, starting now in the correct way. It's starting in going forward in time, starting with a study population. You then find out who's the exposed, who's the unexposed, and then whether or not they go on to develop disease or not. And then you can compare the disease rates between the two groups. That gives you the relative risk of that exposure. So how do you know which one to use, cohort or case control? If the members are easily identifiable, if the members are easily accessible, and if the exposure is rare, you go with a cohort. However, if the disease is rare, or it's very difficult to find lots of people, that's when you go with a case control. And lastly, you have your experimental designs. This is when you're testing the effect of an intervention. Okay, usually it's randomized, although sometimes ethically not all clinical trials can be randomized. But it's the highest standard for, or one of the highest standards for experimental design. And the reason is because of the validity. It has the highest validity because the randomization is what really knocks out a lot of the bias. When you're talking about randomization, you're talking about the randomization leaves out selection bias. That's number one. But it also has a tendency to distribute the confounders equally between two groups. And so that eliminates a lot of the confounding bias. If you double blind it so that that both the patient and you don't know about the treatment or the intervention, that alleviates a lot of the observer bias or the study bias. So that's one of the reasons why it's one of the most powerful, because it's the most valid. It eliminates a lot of the biases, but it's expensive. Requires a lot of time and a lot of R01 grants. So what do you get out of all these clinical trials? What are you going to get from the measurements? Cross-sectional will give you the prevalence. All right, but that's just it. Your case control allows you to determine the odds and the odds ratio. And we're going to go over a little bit about that in statistics. Your cohort is going to give you, for the most part, your incidence. And when you talk about what's the best study to look at incidence, it's a cohort group. It also allows you to calculate the relative risk. And then lastly, your clinical trial will also, if it's big enough, can give you an incidence as well as relative risk, but also tells you things like absolute risk reductions and number needed to treat. So now we get to go on to statistics. So we've learned about all the studies. We've talked about, so what do we do with them? Now we're going to start with definitions again. All right? Type 1 error. All right? When you assume that there is actually a difference, but there actually is none. So when you think the study links one thing to another, but it actually does not, that's a type 1 error. The type 2 error is the opposite. So when you think that there is no difference in a condition or in a disease associated with the exposure, but then it actually is, that's a type 2 error. So the type 1 error is, hey, this guy gives a great statistics talk. He must be a great epidemiologist. Wrong, I'm not. All right, that's type 1 error. Type 2 error, let's see. Boy, I've listened to this talk and I'm never going to learn anything about statistics. You're wrong too, that's a type 2 error, because you will. And by the way, hey, I'm doing pretty good, all right? Yeah. The power is the ability of the test to detect the difference. And a lot of people say, does it have statistical power? Does the study have power? The best way to raise the power of a test is to increase the number of subjects in that test. So increasing the N is one way to increase the study power. All right, so here we go on to our 2x2 tables. A lot of times, actually, the boards may actually give you a 2x2 table for yourself. But in case you actually have to put one together, the way to do it is in your columns, first is disease present, then disease absent. And then in the rows, first is test positive, test negative. So that your upper left corner is all your true positives, those people who test positive and actually have the disease. That's in the upper left of the box. In the lower right is your true negatives. The test is negative and the disease ain't there. So you put that together, and this is when we're going to be able to do the basic statistics, and they're not going to be asking you to do a lot, but they're going to be asking you to things like sensitivity. So sensitivity is the likelihood that the test is positive when it's supposed to be positive. So that's basically your true positives over all of all the people who have the disease. All right? When you're talking about sensitivity and specificity, think about the columns. All right? Sensitivity is A over A plus C, basically just going up and down the column. The same for specificity. Specificity is the number of true negatives out of everybody who doesn't have the disease from that test. So D over B plus D, basically that second column. When you get to the positive and negative predictive values, now you're going by the rows. So think about predictive value as the row. The positive predictive value is the number of people with a positive test who actually have the disease. So it's the true positives over everybody who tested positive. So basically going across the top row, A over A plus B. Conversely, your negative is the people who were negative divided by everybody who had a negative test. So D over C plus D. That part makes it a little easy. Odds ratio is a little bit harder though. All right, the odds ratio, remember, coming from the case control study, is the odds that an outcome or disease in the exposed group versus the unexposed group. All right, so it's A over C divided by B over D, which if you just did the cross product is basically A times D divided by B times C. The relative risk is a little bit easier. The relative risk is the probability of an outcome in the exposed group divided by the outcome in the unexposed group. So the people who have the disease in the exposed group, A, divided by all the people who were exposed, A plus B, divided by the number of people who have the disease in the unexposed group, C, divided by C plus D. And between those two, you'll be able to get the relative risk. It's just the ratio between the two. So, putting together this question, which of the following studies would be best determined for prevalence? And if I haven't beaten this into you already, I got another 5 minutes to go. All right? Is it the cohort? Is it the cross-sectional? Is it the case control, or is it the randomized controlled trial that will give you prevalence? There you go. All right, the cross-sectional study gives you the present, which is and this is, unfortunately, they always say, what is the best? All right, yeah, you could probably get it from a randomized controlled trial, but that would have to be a huge trial. So the best study for prevalence is cross-sectional studies. Let's talk about a new rapid screening test for influenza. The test was administered to 1,000 children with the following results. I actually populated the test for you. You can thank me later after the talk. So, 50 true positives, 600 true negatives. False positives were 300, false negatives were 50. What is the sensitivity? What is the sensitivity? There we go. We didn't even use a smartphone, right? Easy. 50 over 50 plus 50. All right, going down that first column is sensitivity. A over A plus C. 50 divided by 50 plus 50 is a 50%. All right, specificity. What are we going to get with that? If I wanted to do specificity, there we go. Excellent. 600 divided by 300. I'm sorry, 600 divided by 300 plus 600, which is 900, right? So there's your specificity right there in the bottom, okay? The 600, which is your true negatives, divided by the 300 plus the 600. That's simple. So a lot of what you're going to be asked for is basically which study is best to use which simple calculations that you're going to have to be able to make. They're not going to be making things hard. They're not going to be making you do long division. They're just going to be asking you whether or not you know some of these basic statistics on the exam. All right, and with that, I want to thank you for your time, and I appreciate your attention.